All right. Well, good morning, everyone. Apologies for the delay here. I had to uh, sort out the um, audio on this webinar. Anyway, thank you for joining us on our first U.S. webinar, maybe second U.S. webinar of the year. This one's focused on another area that's vexing to the wider industry and policymakers. It's industrial decarbonization, and it's really a focus on the hard-to-abate sectors. Thank you for joining us. I will be supported by Sarah, who will be managing your questions. The format of these webinars is that I'll present some of the information, and then we will have Q&A at the end, and there's also an opportunity for you to vote on what you think should be our next topic, which will be happening in May. So in terms of the topic for today, we're going to review the U.S. and state CO2 targets. We're going to identify what the current level of fuel emissions and associated, fuel consumption and associated CO2 emissions are. And then we're going to examine some of the key end uses and the industrial electrification pathways for decarbonizing them. And then we'll end with an outlook as to how we see, or how the world, I guess, or the U.S. sees these pathways evolving over time, and then we'll finish with a summary of key takeaways. If you have to leave early, or if you want to share this with your friends, as Sarah has said in the chat, there will be a recording made available, which will be sent out in the coming days. Without further ado, I'm Ezra Beeman. I'm Managing Director of Energeia. We've got offices in California and Sydney, Australia. So let's first talk about where we are at the moment. I mean, the U.S. has, up until recently, and is still technically a signatory under the Paris Agreement, which is looking to reduce emissions levels to 50 or 52% below 2005 levels by 2030. Now, the new administration has come in and begun the process of withdrawing from the Paris Agreement, which is expected to take effect around 1 year from the submission on January 20th, 2025. But however, many states have committed to something significantly higher. And so I think in the near term, at least, that's probably going to be the focus of most activity related to the discussion today. You can see here, these were updated since our last webinar, talking about them using 2023 EIA data, that the current baseline forecast for emissions in the US shows that industrial and transport, and bear in mind, only some of transport's really sort of heavy duty that we'll be covering today. Much of it is just a standard sort of light sedan or even medium duty trucks. But even so, the material we're covering today could account for up to about half of the emissions of the United States. You see here, and we've picked out a couple particular states, and you see the breakdown of emissions here between residential, commercial, industrial, transport, and electric power, and it varies quite considerably between the states, with Delaware having the largest share of industrial emissions, and probably Massachusetts or Maryland having the smallest share. You can see the proposed trajectory, and this is all pre the new administration, that sees a little bit of an inflection point around now to get us to either zero carbon by as early as 2045 or as late as 2050. And I believe California and Maryland, for example, are some of the two that are at the moment committed to an earlier zero carbon or zero carbon from baseline outcome. So as we said here, the key question is, how much is this going to cost the industrial sector to transition, and potentially what sort of CO2 price level is going to be required to get there? Right, so let's talk about where these emissions are largely gathered. Top left graphic from the EIA again shows the different levels of energy consumption by the type of energy that's being consumed across most of the heavy industry sector, and these industry sectors are defined by NAICS codes. Now, different fuels will have different emissions profiles. And you can see on the bottom left that refining and bulk chemical are nearly double that of any other sector. I think the refining sector itself is going to look very different if under a decarbonized world. And so really what you need to focus on are the harder to abate sectors of chemicals, cement, iron and steel, aluminum, mining, and manufacturing, or heavy manufacturing. It's really where electricity or electrification is not a ready-made substitute for what's going on, or the processes themselves create or need CO2. So let's talk about some of the CO2 pathways for some of these hard-to-abate sectors. And there's a lot of words here, so apologies for that, and we did really try to reduce them, but I think it's pretty important to understand exactly what is about each of these sectors that's hard to abate. So let's start with iron and steel. You can see here that the conventional iron reduction process uses very high heat and the direct reduced iron method to produce liquid iron. And we're talking temperatures over 10,000 C, I mean 900 to 1650. And previously that was mainly done through gas firing, etc. And that's because it is cheaper. It is cheaper overall without a CO2 price to do it in this manner. And so you either need a new kind of process, and or you need to be able to bring up the current process to these levels. And then there's also the CO2 involved in the process. A similar but different story for cement. You need, again, very high heat of 1450 C to produce the clinker. And there's also the natural escape of CO2 from limestone, and so that would need to be either offset or captured during the process. Aluminum, again, it's a high heat process, and there's a reaction with carbon to achieve this, so there has to be some carbon into the process, and so this will need to be addressed in the aluminum production. Chemical and petrochemical, I mean, there's many pathways here. We call out the steam cracking of hydrocarbons and aromatics, using catalytic reforming, etc. And again, high temperatures and also the use of petrochemicals as feedstock into different other chemicals. And so this is going to have a different feedstock, and any sort of heating will have to be done with something that doesn't emit carbon. Mining, you've got an energy intensive processes. A lot of this is really just traction, crushing stuff, moving things around and doing it in the middle of nowhere. We're seeing a lot of progress in these areas because you can string a wire out there, and actually these large trucks don't really move that much. So yes, it's expensive, and if you do it with renewable energy at the moment, and you need to do it 24/7 with the firming, it can be more expensive, but those costs are coming down. Heavy duty transport, anything from cement trucks to long haul big rigs. It's usually the combination of distance and weight that makes it difficult for current battery technology to provide the same level of service. Then we get into shipping, again, when you're going long distances with great weights, and so the energy density of the fuel becomes an issue. And with aviation, it's not density, it's just how much it weighs relative to what you have to do. Although, you know, in drone technology, et cetera, we're starting to see electric alternatives emerge. So different heavy industry and transport applications here that are traditionally considered to be hard to abate, that have to find a solution if we are to decarbonize and hit the Paris Accord targets. So what are the potential solutions here? So we mentioned, well, one, of course, is always going to be energy efficiency. That's just doing the current processes and methods with less energy and generally less CO2 emissions. That's going to be a great early opportunity, but it's not going to get us all the way. Electrification can suit many of those applications, certainly on the heat side, and the heat technologies are improving in their energy efficiency and their costs are coming down. But there still may be a need for either CO2 in the process or other petrochemicals in terms of molecules that will need to have an alternative, and an alternative that is zero emissions. There's alternative processes, some were spoken about just previously, and then there is alternative fuels, things like green hydrogen, which is made from electrolysis using renewable energy, biofuels, this is anything from biomethane, biodiesel, etc. And sort of the catch-all that if you're not able to do all of the above is to use the CO2 in making roads or other kinds of building materials or burying it. And then finally, there's the offsets of potentially changes in land uses, forestry, etc. So that's really the slate of technologies or approaches that the world has to decarbonizing. And we've got a simple tick chart down below, which is hopeful in that many of these things apply to all of these sectors. What's missing is the cost and also the volume as to how much green fuel or biofuels are going to be available and how are they allocated across these different sectors. Yeah, so I guess in summary, energy efficiency will get you so far, maybe 10 to 20%. There are green fuels that can be used in place of diesel in particular, but also methane, RNG, etc. But there's only so much green biofuel feedstock that's available until you start growing it specifically for that, and then it becomes prohibitively expensive. And then from there, it's really hydrogen, alternative processes, and barring all that, it's CCS and offsets. So let's dig a little bit deeper into those for these specific hard-to-abate sectors. So this is not everything you can do. This is the results of a lot of research by the team to really just gather together what is the state of the art in our understanding of what the key options are and what the relative costs are. So in the case of iron and steel production costs, you could use an alternative reducing agent, for example, hydrogen. You could electrify the boilers using things like arc furnaces and arc plasma furnaces, which can get the temperatures up to 10,000 degrees C. Barring that, you can do carbon capture or use an alternative smelting reduction process. Now, if as an investor, you'll want to choose the cheapest thing first, and right here we're showing the alternative innovative smelting reduction process at about $300 a ton. Now, this is much higher than some of the CO2 prices that we've seen. And even this, but showing here the CCS is at $420 a ton of CO2 equivalent. This is a reflection of the cost mainly of capturing the emissions through the process and utilizing it. And you see below here for aluminum that the carbon capture and utilization and storage is only $8 a ton. So it's important to bear in mind that there are very significant differences between these two industry sectors and how you would actually capture that carbon throughout the process, and it can lead to very significantly different costs. So the other thing I'd point out, and this is something that we didn't really see in the assessments to date, is some of this stuff, whether it's the innovative smelting reduction process or the alternative reducing agent, some of these represent significant investments in alternative processes. And if you were to rip out the existing equipment and put this in, this is the kind of cost you'd be talking about. If you do it when this equipment is at end of life, it's a very different story. And this is actually some work that we're hoping would be taken up into the future to really look on a marginal basis when this equipment is likely to be end of life. what is really the marginal cost of this activity? Because that's going to show, in our view, a very different perspective on things, and one that I think would allow policymakers, investors, and industry to really better sequence this and to do it at far lower cost than some of these numbers are telling us. But that involves more investment and more analysis than what we've been able to identify. All right, turning to cement production. Here again, electrification at a whopping $1,798 per ton is just really out of the ballpark here. Then we have CCS and some improvements in thermal energy efficiency. Now, of course, those relatively low costs for improving thermal efficiency looks great, but it's only going to get you so far. CCS looks to be the pathway at the moment that's going to get cement. And I know there's green cement out there touting that they're going to make this happen. I've not really seen a price tag associated with them. And we weren't able to find any particular examples to bring here. But there's a wide gap here between the CCS and electrifying the process heating. Petrochemical and chemical production, more options and more graduated, but even the cheapest one here with CCS it's coming in at about $1,353 to capture all of the carbon here, which is a pretty high price tag for fully decarbonizing these sectors. So again, this raises the attractiveness of things like LULUCF, which is the offset sort of approach, and one that Australia is pursuing heavily. But there are alternatives to offsets through sustained, targeted policy focused on R&D and ongoing investment in this area. You can see some of the dates on this are back in 2022. It's not enough for governments to have done this with one stage and be done with it. It has to be an ongoing effort. So we get to the transport areas on the heavy transport, cement trucks, etc. Battery electric does look like it's cheaper. It won't suit all of the applications. There's the biofuels, whether it's ethanol, and then going to green green hydrogen and fuel cell electric vehicles, which are orders of magnitude more expensive than EVs, but may be required for the heaviest transport. And then shipping, you've got electric ships, relatively expensive, and then biofuels, but limited fuel sourcing at the low end. And then aviation, e-fuels are drop-in replacements, but you can see here relatively expensive compared to electric planes, which are still in their infancy. So it's not a pretty picture in terms of decarbonization, certainly not the same as building electrification or light-duty electrification. This is really where the rubber meets the road, and the world, the country, and the states really have to work together and put a lot more effort into bringing these costs down through R&D, through knowledge sharing, and through better targeting these solutions to when the equipment needs to be replaced. If we continue to invest in the current equipment, it's just going to push that out. We may be able to bring costs down in the meanwhile, though. So just quickly, and I want to make sure we've got time for questions for those who have to run off to the next thing. You see here, it's very difficult to get a carbon price forecast. They are just not out there for the long term, which tells us something about how much investment's going into this sector by policymakers. You see there's a view here that we're going to start ramping up on the price from about 2027. You can see here there's a slight kink in most of these from a trajectory that was sort of going like in one rate of change, and around 2027 changes, and you're going to have a price to get that up. But looking at biofuels, now these are measured in terms of the cost net of the alternative. So if you're a liquid fuel relative to diesel, if you're a gaseous fuel relative to natural gas. And over time, this is work we did 2 or 3 years ago. It needs to be updated. Green hydrogen costs have not come down like we had expected. So this sort of work, like the other work that we've seen, all really needs a refresh. And I think that's one of the key messages that we're delivering through this webinar is more work is needed. This is still half of or more of total emissions, and the amount of research, analysis, and ongoing focus in this area really is not commensurate with the risk and costs involved. Here we have the CCS. I mean, this I think is widely viewed as the relief valve. Hey, we're just going to bury it. I know that projects to bury it in California anyway are just at their infancy. So we're betting the farm on having it on a technology that still remains to be demonstrated. Certainly at these cost points, there's a wide range in offsets. These will have to be done largely in other countries. And again, the costs and the effectiveness of these, I think, is still somewhat open to question. So here's a current cost point and a future cost point. Yes, it looks like biodiesel and renewable diesel with those old, probably out-of-date forecasts are going to be cheaper. They're certainly limited in supply. And so as a policymaker, focusing on bringing down the higher cost elements, which are not even shown here for specific things like high temperature heat or the process improvements. Those are very sector by sector specific. Even CCS, which we're showing you an average number here for the sequestration or bearing cost of it, can still come down and is relatively immature, and more work needs to be done. Okay, so in terms of key takeaways and recommendations, what we've just reviewed still represents the lion's share of CO2 abatement, and there's a long way to go. Large portion of them are not necessarily suited for electrification, although particularly high temp electrification does appear to be improving in efficiency, and that means cost reduction. But we'd like to see more demonstrations and targeted cost reduction in that area to really make folks pay more attention, because there'll be equipment that comes up for renewal every year or every 5 years, and it's really important that there's a viable demonstrated alternative for them to turn to. While specific solutions are being developed in each of these sectors, they can be very high cost, especially on a standalone basis. The CCS, CCUS offsets are general approaches that may be needed to achieve abatement targets. And at this stage, we don't have a lot of confidence in the numbers that we've seen in terms of their availability and also their price. So our recommendations are, first of all, review what's out there in terms of the programs, the funding, and ensure they are commensurate with the looming cost and need. Electric high temp heats are key solution that will be essential to the transition. R&D really needs to continue and needs to be invested in if we are to manage the associated risks. Biofuels look great. There's not enough of them, and those supply chains have been relatively slow to develop, only because the level of demand hasn't really been there. Green hydrogen is going to be needed. We're going to have to continue to progress it. I think there's been a general pullback around the world in green hydrogen because maybe it was being targeted at everything, and everything is not cost effective. And then finally, so much is riding on CCS and LULUCF. So really, we need to be certain that these are viable alternatives before we bet everything on them. Well, thank you so much. I realize we are at time, but if you are able to stay for a couple of minutes, happy to answer some questions, but I look forward to the questions. Okay, first question: are these forecast abatement prices, especially for emerging technology, reliable? I think they were reliable when they were made, at least the ones that we developed. We know they were based on a lot of analysis that had led into them. The fact that it's now 3 or more years on means that things have changed, and so they probably are no longer as accurate as they could be, and certainly another round of investment in bringing the state of the art, collecting our understanding of the state of the art, I think would be valuable for everyone, for policymakers, for industry, and for analysts like ourselves. How much of the low-cost pathways are there, and how will they be allocated across sectors? Um, Again, we've seen previous work at estimating the supply of biofuels, RNG, et cetera, and it tends to be an upward sloping supply cost curve, certainly for biomethane, because there's just so many large scale dumps or farms, abattoirs, et cetera. And so as you work your way through the mega ones, then you have to go smaller and smaller, and it becomes more and more expensive. And we haven't seen any major new work, I don't know, in 5 years or more. So, don't really know. It would be good to have this be an ongoing activity to make sure that there is common understanding of how much there is, because then we know how much we need to do using something else. What would you do in the near term to minimize the cost of the hard-to-abate transition? Well, I think I've been trying to um, say that throughout this webinar, which is the industry needs to focus on the low-hanging fruit, energy efficient investments where they make sense, and I guess undertake their own R&D to see which of the alternative solutions is going to make sense for them as major equipment is end of life, to consider the alternatives, and if everything's working relatively well, to be able to create CO2 certificates, so that they may be able to offset any differential in cost for new equipment using those CO2 equipment certificates. But I do fear there's going to be a mismatch between when the equipment comes up for service, what the CO2 price is, and industry is going to be potentially forced with investing in the same type of technology and looking to then either use offsets or CCS to deal with that in 20 years time. So I think that's one of the key risks here, and a lot more work is needed to make sure that everybody knows what the alternatives are, what the net incremental costs are, and what the net sort of premium or subsidy or payment needs to be to make industry see the decarbonized pathway as no more costly than the business as usual pathway. All right. Well, I think everybody has had to move on to the next thing. So we'll wrap it up there. Please don't forget to vote if you haven't already. And we look forward to seeing you at our next webinar, which will be on bridging the skills gap, workforces for electrification. Thank you very much for your attendance and attention, and I look forward to seeing you next time.